Okay, so like I was saying, this is going to be the introduction of X86-64 instruction set. Last time we talked a lot about the registers, because the registers are bewildering and confusing all by themselves. But we had these registers, 16 general purpose registers, which is really great. Up to IA32, we only had 8 general purpose registers, and really we kind of only had 6 because you can see that RSP and RBP are in there, so we had ESP, EBP, and you kind of couldn't use those for other things, and so you ended up only having like 6 nice, useful general purpose registers for doing things. So having the additional 8 registers suddenly is luxurious, and in fact, all of the coding in CS24 in assembly programming, once we switched over to 64-bit, became a lot easier. And so I was like, oh, I should make the assignment problems harder, but I haven't because I don't want to be a dick. So, but anyway, you'll notice that we have these registers. Remember, there's things like RAX, EAX, AX, and then there's AH and AL. There's all that kind of malarkey that you can look at as well. Okay, so I'm not going to cover too much of that. We're going to dive right into the instructions, which follow the same general pattern we had before. Opcode, or the text representation of the opcode, and then what are the operands to the instruction. And since this is a CISC architecture, it goes all over the place. We have all kinds of wild things we can do with the operands. Here are some simple examples. Anybody here? Well, so 5x isn't a thing anymore, right? Well, who still took 5x before it died? Okay, cool. So did I, represent all that kind of stuff. I loved 5x. This is AT&T syntax. That's exactly correct. Anybody reading the slides will also see this. This is AT&T syntax, which we use exclusively in this class because that's what the textbook uses. Okay? And so if you don't like it, I'm sorry, but you'll live. I have done both. I've done a lot of assembly programming both in 5x and also on my own for funsies. And honestly, I like AT&T syntax better than Intel syntax anyway. There's only one area where AT&T syntax is annoying, and that is when it comes to compare operations. And we'll talk about that more in future lectures. So I'll show you exactly how it's brain damaged, and I'll show you how to understand it. So don't worry about that. The thing to be aware of, though, is that the Intel manuals use Intel syntax. Different order of operands, so just make sure you pay attention to that when you're understanding the manuals. One of the things that I'm trying to do in this class and many of my classes is make sure that you learn how to get answers to questions on your own without having to go and ask another person or have somebody handhold. I mean, that's like such a powerful capability to have in real life. And so I'll point you to the Intel manuals. You should learn how to read them when you run into new instructions. But I think I don't see it in this, but if you run into an opcode you just cannot understand, ask me or ask the TAs. But you should be learning how to use these resources because it's very powerful to be able to go get answers on your own. Okay, so yeah, this is the difference. Like I was saying, the order of operands is in a different order. So AT&T, things cleanly move left or right, which is how we read things. So RCX moves into RDX, whereas on Intel, the destination or the target is the first operand. Sorry, okay? This is assembler level stuff. I mean, obviously the machine code is identical, but AT&T syntax is a little bit different. Okay? I'll also mention just in passing that like if you're looking at the Linux kernel and how Linux works, sometimes you run into assembly code functions, or you decide to take 124. We use AT&T syntax for that. Linux uses AT&T syntax, so it's good to be familiar with it and to be flexible about this kind of thing. Okay, let's see. Many different categories of instructions. We're going to talk about a few of them today. Data movement, arithmetic, logical operations, and flow control. That's kind of all we have time to talk about today, and we actually kind of don't even have time to talk about those, but we'll do our best. These are the various data movement operations. Move, I don't know what they have against e's, but they took off the e. So you have move, and then you have move with sign extension. Remember how we have that top bit can be the sign bit if we're working with the signed 2's complement value. So if we're moving and we're moving from a smaller width value to a larger width value, then we need to extend the sign. Or maybe we don't care because we're doing unsigned, then we can do move with 0 extension. and then obviously push and pop as well. Okay, so we have these various things. Now, if this is scary, it gets much worse. So I just wanted to give you a heads up that this is going to get fun really quickly. Primarily because we have all of these suffixes that we can put on instructions. Now, it turns out that the suffixes are mainly for human beings because it's hard enough to read assembly code, so you can put little suffixes on that say, this is the size of the thing that I'm working with. And you'll notice that it already goes squirrely because you have B for byte, that makes sense. W for word, remember X86-64, that's 2 bytes, always, no matter what data bus width you have on the processor. L is double word. Okay, not D, which would be really nice. And then Q is quadword, okay? So that'll be 8 bytes. Now you have certain instructions that move just with, work with one data width. And so if you were, for example, moving from CX to DX, you could say move W. Do you need to say the W? No, you don't. But it's sure nice to see. Okay, because when you're tired and trying to debug assembly code at 3 in the morning, which I know none of you will ever have that experience, it's really nice to see the suffix so that you know what in the world you were thinking. Okay, push Q, RAX. Okay, so that pushes the quad word or 8-byte value from RAX onto the stack and so forth. Okay, now moving with sign and 0 extension starts to get really nasty. So here I'm moving a byte value into a long word or 4-byte value. And so AL goes into EDX, and I sign extend AL. So if AL was -6, well, now EDX is -6. Yay, for us, right? Okay. So that does sign extension. This is move with 0 extension from a 2-byte word into a an 8-byte quad word. And so you're moving CX into REX. Again, you don't have to say those suffixes, but it's just nice. And so you'll probably get some squawking from TAs if you don't do it. Okay? There's only one part of this class where you don't have to specify, or you get code from me that doesn't have suffixes, and it's the stuff you have to debug. It's the debugging problem. So it's like, have fun. Yes?
So does move without S or Z mean they have to be the same size? And if not, what's the difference between move Z and move?
That's a very good question. If you are moving without S and Z, do you have to have the values be the same size? And yes, the assumption is that they are going to be the same bit width. Now, there's a few caveats to that, which I'll show you momentarily. If you're moving like 6 into RDX, well, you can do that, even though you know you can represent 6 with 1 byte. The assembler will be clever, because remember, this is a CISC processor, and so it has fancy instruction representations. But yeah, in general, if you're moving without sign or 0 extension, the assumption is the operands are the same width. Okay? Does that answer all your questions? You also asked about S and Z, and I can't remember if... I mean, obviously, like move S and move Z don't make any sense if the source and target are the same width. Okay? All right. Let's see. This instruction, what do we have here? Move with 0 extension from a 4-byte value into an 8-byte value. So we're moving ECX into RDX. This is not supported, which seems a little bizarre and baroque, or maybe just broke, but there's a really good reason. X86-64 does something really nice for you. Anytime you write to a 32-bit register, it automatically 0 extends into the corresponding 64-bit register. So like I have here, if I move from ECX into EDX, well, what happens is the top 4 bytes of RDX are automatically zeroed. Okay? There's all kinds of good reasons why this happens. It's to make sure that 32-bit code works okay on 64-bit processors. It also greatly simplifies a lot of the operations where, let's say you have an int variable I. Remember in C, you have int I and you want to iterate over an array? Well, it turns out that even though that int is going to be 4 bytes, you still need 8 bytes to specify the offset into the array for doing address calculations. And so the processor helps you out a lot by always setting the upper 4 bytes. Did I get that right? Yeah, the upper 4 bytes to 0 when you write to a 32-bit register. Okay? That'll become your friend really fast, I promise you. Okay, if you move a constant into a 32-bit register, that also clears the upper 32 bits of the register. So move 10 into ECX. That automatically sets RCX to 10. Okay, see how simple that is? So you can see that already you can do certain things to simplify your life. But it does require more sophistication in your understanding. One of the things that I told the TAs last year, and they all heartily agreed with me, is that moving from IA32 to X86-64 is a little bit challenging because the computational model on IA32 is simpler. Like you can already see, well, if you've got these built-in side effect thingies that happen, well, that's more mental baggage that you have to keep in your head when you program the thing. But the nice thing is that X86-64 actually results in shorter code because the processor is doing more things for you. So that's kind of the challenge, the trade-off that you get between IA32 and X86-64. IA32 is simpler to understand, but you have to write longer code. X86-64 is a little bit more complicated to understand, but your code gets shorter. And honestly, I like short code because it means there's less likelihood of bugs. That's a pretty well-established observation. Wait, I think I forgot to talk about this last thing. Oh yeah, move with sign extension from 32-bit into 64-bit. Because, I mean, you don't need move with 0 extension, so move with sign extension is still available if you need to do so. Okay? All right. Let's see, operand types. So there's a bazillion of them. You have immediate values, which confusingly require a dollar sign in front of them. So if you just have a number by itself without a dollar sign, guess what? It's a pointer. So don't do that. Just make sure that you do a dollar sign in front. I don't know why they chose that, but that's what they chose. Okay, so there's a little bit more brain damage in the AT&T syntax. $5, whatever. And you can also specify hex values if you wish. Registers have to have a % sign in front of them. You may ask the question, like, why in the world would I require a % sign in front of a register name? Well, because this is an assembler we're programming, and you can have variables that are in memory, and you can refer to them by name. So we need a way of distinguishing between variable names and register names. Okay? So here's an example, move Q, $42, because we just love 42 so much. Let's move that into RBX. And really, honestly, all you'd have to do is move it into EBX, and it would clear the top 4 bytes of RBX for us. And so you can see that that's the way to write that instruction. Okay. Now, this is also a really good illustration. If you were to look at the encoding of this instruction, you would see that it only stores 1 byte. So technically, it's moving 1 byte into an 8-byte register. But that's just a characteristic of the instruction encoding. Conceptually, since it's just doing a regular move, we're still moving you could consider it being move a 64-bit constant into the 64-bit register. Okay? Everybody got it, I hope? Yay, all right, we're all keeping up. Okay, memory references. Again, bewildering at first, but so powerful it makes code so easy to write, indexing into arrays of longs or whatever we want to do. Okay, so we're going to denote memory addresses as capital M and then the address, just like we did earlier in the course. And so if you have a number without a dollar sign, that is just an absolute address. Okay, so it's going to go ahead and access whatever is at memory at that location. Okay? This is extremely uncommon. Okay? People basically never do this because why would they access a specific memory address? Okay? Most of the time we do indirect memory access. I call malloc and I get some memory back and it's the pointers in a register. So now I want to use that register to access the memory contents that I just allocated. Okay? So you just put parentheses around the register name. So what this is doing is moving 2 bytes from CX into the address that's contained in RBX. Okay? Now the thing is that when you are accessing stuff, with parentheses and so forth, that's got to be a 64-bit register. It can't be a 32-bit register because we're running on a 64-bit processor. Okay? We'll get into a lot of the vagaries of that when we start talking about virtual memory, but just keep that in mind. You can't do like EBX in a move instruction that accesses memory. Yes, question?
What's the difference between that move W from CX? Like, what would be the difference if we had the same command without
If we had the same command without the parentheses, then first of all, the assembler would probably squawk at us because it's saying you can't move a 2-byte value into an 8-byte register without saying how to handle the sign or zero extension. So that would be probably the number one thing you'd run into, is that it just wouldn't assemble. Yeah. Yes?
If the value in RBX is not word aligned, what will happen?
So this is an interesting question. What if RBX is not a word-aligned address? We haven't talked about that yet, so I'm going to punt on explaining what that means. We'll talk about it in a future class. But X86-64 supports non-word-aligned access. It's just slower, and we'll talk about why when we actually introduce the notion of alignment. Okay? Alrighty. Yeah, this ain't no Motorola processor crap. Okay. Yes, I've dealt with those. So here's base plus displacement. So now you can say I want to take a register's contents for the address, and I want to add on a constant. Okay? So this is the way that we do that. I'm going to try to speed this up just so we can get through this all. This is really helpful for accessing struct members, because you might have a pointer to the start of a struct, and then I need to add an offset to get to various fields in the struct. So this is really helpful in those circumstances. Okay, indexed memory access. So now we're actually starting to get into arrays. Think arrays of primitives, not arrays of structs, because arrays of structs are a little bit crazy to access. They're not terrible, but they're just a little crazy. Okay, that's where the LEA instruction becomes really useful. If you see on the assignment LEA, where would this ever be useful? Well, it's useful when you are accessing arrays of structs and so forth. Okay, so here we have two registers. One is the base register. That says where things start in memory. And then the I, reg I, is the index register. So that tells us how far from the start. Okay, now this one is really simple. This is just for, I don't know that I talk about it right here. I'll just explain it really quickly because I talk about it a little bit more in the future. This is if your array was an array of bytes. Okay, so it just adds the two together. Like it says here, accesses M, reg B plus reg I. So if you're accessing the contents of a string that's not Unicode, then that would be perfectly fine. Okay? You can also add a number into that if you wish. I don't know why one would, but one could. And yeah, so like I say here, this is for indexing into arrays of bytes. So a few simple examples just contrived so that we can practice this junk. We can pretend we're a processor. Move Q, REX, RBX into RDX. Okay? Just add them together, right? So we end up accessing the memory at address 550. Okay, and that value, Q, so we have a 4-byte value. Did I get that right? No, I probably didn't because L is 4 bytes. Q is 8 bytes. So 8 bytes are moved from that location into RDX. Okay? Move Q, RCX minus 200. So, wow, this isn't very much more exciting than the previous example. It's just RBX is now the base. So it's just now 400 plus 150 minus 200. Okay? So you can see exactly how that works. Any questions? Okay. Now, if we want to access, you know, like, who cares about bytes? I mean, everybody really cares about bytes because welcome to the internet. We have to shoot bytes everywhere across the internet. But a lot of times, I might want to have an array of floats, or, you know, you guys are used to that, or an array of longs, or something like that. So the processor has built-in mechanisms for accessing arrays of elements whose sizes are not just 1 byte. So you have fun things like this. Again, like this syntax is on the verge of making my eyes bleed, but you have open paren, comma, and then reg. That's the index, that's the offset in the array, but really it's best to think of it as an index, multiplied by the scale. Okay? The scale can be 1, 2, 4, or 8. You can add in a constant if you wish. So immediate value, then open paren, comma, reg, and that's your index. So that would be accessing an array whose elements are 1, 2, 4, or 8 bytes that starts at a constant address if you needed to. Here's the more interesting one if you wanted to start at a base register. So reg B would be the start of your array. Let's say it's an array of ints, so we have 4-byte elements. And then reg I is the index, and S is 4, or whatever you need it to be. So this starts to make your assembly code really intuitive to understand because reg I can just be the index, right? So 0, 1, 2, 3, 4, 5, it just increments. You don't have to worry about doing 0, 4, 8, 16 so that you can make sure you access the appropriate int or whatever. I mean, it's the assembly code takes care of it for you. The processor just does this stuff for you. Okay? Here's another one if you want to add in a number. Okay, now we're just getting into crazy talk. Okay? So REX 150, RBX 400. So what are we doing here? Okay, remember this is in the index register position, so we just take REX, whatever its value is, multiply it by 4. Okay? So this is going to access address 600. Here's another one. Oh, now it's getting nasty. Okay, so RBX is the base register, so we just take the value of RBX, add in whatever the value of REX is times 2, because that's the scale, and then throw in 350 for good measure. Right? Okay, so that's what this does. Any questions? All right, this stuff is so cool, and I almost always make sure that the midterm has some, not terribly miserable, well, at least I try, but, things to do with memory access. Access this array of structs, do junk with it. So it's really good to get familiar with this stuff. Yes?
Just confirming, so the third and fourth bullet point, are they pretty much equivalent syntax? Sort of equivalent. Maybe it's going to accomplish the same thing.
Are you saying like the reg B, reg IS, and im, reg B, reg IS? Well, yeah, I mean, there is an overlap. There's an overlap between the first two as well. I mean, it's just that you add in an additional immediate value. That's really all it is. Okay? So you can imagine that the machinery on the processor knows how to take all these things, like 4 parameters. Immediate value, base register, index register, and scale. And it just computes the thing it's supposed to compute. And then the opcodes are allowed to optionally include or exclude based on the patterns that we've shown in the lecture slide. Okay? So the hardware is able to handle any of those patterns. Okay? All right, so this is the summary chart. The only thing that's really frightening, and in fact, this is not really the best chart because it excludes R8 through R15. So I should probably kick this slide to the curb. But the important thing to note on here is that you cannot use RSI as an index. I mean, RSP. That would be really dumb because RSI is literally an index register. But RSP you're not allowed to use as an index. Okay? So this is of limited usefulness. Sorry that I don't include R8 through R16. Or R15. Okay, let's see. There are important constraints. First of all, the source can be an immediate value. I hope everybody knows what I mean when I say an immediate value. It's identical to saying it's a literal. Like 9. Well, let's say $9 written in your program, right? So it's just a number that you put in there. It can be a register. It can be a memory location. Okay. The destination cannot be an immediate value. That would not make any sense. I don't want to set 9 to be 5. That wouldn't make any sense. So the destination can be a register or a memory location. The one caveat is that both arguments cannot be memory references. That's the weird thing. But I mean, it kind of makes sense. That's just a constraint that the processor has to deal with. Now, there is one weird exception. Okay? Push and pop access memory. You can push a memory value. You can do an indirect or direct memory access and push that value. And you can pop from the stack into a memory location. Okay, that's the one exception to the whole rule of both operands cannot be memory references. Otherwise, and I see this every year. Some student says, I can't get my code to assemble. I don't understand why. Well, the source and the target were both memory locations. You have to move through an intermediate register. Okay? All right. Everybody got it? Cool. Let's see. Let's go on to arithmetic because who cares about... who wants to think about memory access all the time? There's a whole bunch of arithmetic operations. There's even operations for computing like sine and cosine of floating point numbers. It's crazy what the processor can do. But we're just sticking to integer stuff. Okay, so you can increment, decrement. You can do 2's complement negation. Remember we talked about how to do that. You can do 1's complement inversion or just bitwise inversion if you will. Okay. On the right, you'll see the equivalent in C programming. Okay. You can do arithmetic and logical operations. These are all just fantastic, so useful. Okay. And of course, you can specify the byte width of these things. So decB %CL would just decrement the value in CL. Now, again, you don't have to specify the suffixes, but we really encourage it because it helps understand exactly what what you meant when you were writing the code. And in fact, if you say the wrong suffix, then the assembler will stop you. It'll be like, hey, the suffix doesn't match the operand. Okay? All right, there's that. See, here's another one, add L. So here so this is kind of a fun example because you can see we're accessing RBP plus 16. So RBP is a 64-bit value. We're adding 16 to it, but we're really not adding that value in. We're adding whatever is at the 4 bytes at that address to EAX. Okay, so you'll see operations involving different bit widths because they have different roles. Okay, let's see, shift operations. So you have all of the different kinds of shifting you might ever want. Notice you have logical shift right and arithmetic shift right because one is sign preserving and one is not. Okay, but then you also weirdly have arithmetic and logical shift left. Okay, but they actually assemble to the same opcode. Okay, because they mean the same thing. All right. The nice thing about this is that you can do left and right shift by more than 1 bit, unlike our simple contrived processor that we talked about for a week. So you can either have a constant, which I believe is up to 31, or if you need more, then you can put it in the CL register. Okay. And you might ask, why the CL register? Well, because that's the way it's always been. Don't ask me questions. Okay. That's kind of unfortunately the answer here. You also have rotate operations, which are really powerful. Oh, there's some really cool stuff. I got to write some assembly code for a consulting project a couple summers ago. And you can use rotate through carry. So notice RCL, RCR. So that'll rotate through the carry flag. You can use that for doing rotates across multiple quad words and things like that. So you can actually use this for arbitrary size arithmetic computations. You'll actually notice this, that the X86 processor supports all of the machinery necessary to do arbitrary width calculations, which is sometimes I include a midterm problem on that. I'll see how I feel this year. Okay, multiplication and division. Yick. Okay, so 64-bit value times 64-bit value can be up to 128 bits. That's lame. 128 bits divided by 64 bits. Well, on a good day, we're going to get a 64-bit quotient and a 64-bit remainder. But, of course, I think we all realistically understand that it could be a 128-bit quotient if we're dividing by 1. And the remainder could also be equally nasty. So this is what we hope for. This is what generally the processor supports. You'll notice there's a whole range of different instructions. So we have imul, source times dest. And basically what happens is dest becomes source times dest modulo the bit width. Okay? So, or I should say 2 to the bit width if we're going to be really accurate here. But anyway, you can use this for doing basic multiplication, but it will truncate. And that's kind of the big thing you have to be careful with. Okay? So source times dest, bit width W, the result is modulo 2 to the W, and then that goes into dest. There's also 3-argument multiplication. If 2 arguments is not enough, now that's all the arguments you get. You can't have 4-argument multiplication, not today. But source 1 times source 2 goes into dest. And again, everything is the same bit width, so the result is modulo 2 to the W. Okay? So that's multiplication. Or at least that's what you thought, because there's other crazy versions of multiplication. There's also the 1-argument multiplication, which is actually able to generate a 128-bit value, if that's what you need. So source times whatever's already in RAX ends up going into RDX, RAX. Okay? Now we have this weird thing that I wrote here, RDX : RAX. You see this a lot in documentation. What it means is you take the two registers' contents, concatenate it together, and that's your answer. So RDX is the top 8 bytes of it, and RAX holds the low 8 bytes of it. Okay? Yeehaw! How fun is that? Let's see. So now if imul q and imul, all of our different variants of imul, wasn't exciting enough, there's also mul. Okay, what's the difference? The I kind of stands for signed integers. That all would abbreviate down to I, right? So imul is signed and mul is unsigned. That's basically the distinction between the two. Okay. Now you also have division. Division is basically always one argument. Okay? There's a number of implicit arguments that you have to set up before invoking the divide operation. So notice IDiv, and you can ignore the Q because that's just the size suffix, but IDiv Q if it's going to be a 64-bit register. Source. And basically, source is divided into the combination of RDX and RAX. Okay, so you can take a 128-bit value, divide it by a 64-bit value, and you end up with two 64-bit values, you hope, right? So RAX becomes RDX, RAX divided by the source, so integer division, and then RDX becomes the remainder of that division. And again, you hope that life didn't become really miserable and complicated when you did that. Okay, and so there's also div q for unsigned division. Okay, let me ask you this first. Any questions? Okay, this stuff is slightly crazy talk, and so you can imagine, for example, if you were writing a C program and you had two ints and you happen to multiply like 2 billion times 2 billion, you're going to get a weird answer. And you can see why, right? Because you're going to probably have truncation of the high bits from your result. Yes, question? That is an excellent question. I literally mean RDX, RAX. You have no other choice. All right? So that's kind of an interesting thing. Just like the shift left and shift right with CL, has to be CL if you want it to be a large value. Well, same thing here. If you want to do multiplication or division using a 128-bit value, you have to use RDX, RAX. Okay? Yes? For simple arithmetic, I'm presuming you mean addition, subtraction, logical operations. No. The only 3 argument operation that I know of on the processor is the 3-argument multiply. I don't know why they did that. I'm like, really, guys? I mean, was that necessary? I don't think it was, but they did it. Yeah. Question?
Yeah, so maybe I'm misunderstanding, but it looks like, source is a 64-bit number, and then it looks like we're trying to stuff the product into
16
16 bytes,
bytes would be 128 bits. Okay, cool. Yeah, no, look, this is a lot to absorb, and CS24 is not known for moving gently or slowly, so I get it. I have to review these slides every year I teach them. It's not like I have it all memorized. Okay, how do we set up RDX, RAX? There's a magical instruction called CQTO, of course, right? That makes total sense. It actually isn't called that in the Intel manual anyway, because why? Be clear and understandable. But CQTO converts a quad word into an oct word. So it takes whatever's in RAX and sign extends it into RDX. So you want to divide by -9, or you want to divide -9 by something. I don't know why you would. Let's say you're dividing it by 3. Then you could extend that minus sign into RDX. Now, why is there no 0 extension? Just set RDX to 0. Okay, that's easy enough. All right, now there's a whole bunch of other ways you can do this. Again, I'm going to show you this just because we do work with ints in this class. Ints are 4 bytes. Even though this is a 64-bit processor, we're going to work with a lot of 32-bit values. So imul d, for example, is source. So you get EDX, EAX becomes whatever the source is times EAX. Okay, so notice it's E's instead of R's. Here would be, why do we even care? I mean, this was what I did when I was in high school, because I only had a 16-bit processor. So this was the kind of junk I would do. But yeah, you have all of these various options. Okay, let's see. Convert word to double word. This is, again, if you happen to be stuck in like the late 80s or something, then you can do convert word to double word, and that'll sign extend AX into DXAX, or CLTD. That one might actually be useful if you're working with ints. Okay, sign extend EAX into EDXEAX. Okay, and then you can also just work with parts of RAX if you need to. There's a number of instructions for sign extending throughout RAX if you need to. Why not, right? I mean, it's a freaking CISC processor. Why not? Okay. We have available instruction encodings. I'm just going to make them mean something. Okay, any questions? So you can see that multiplication and division is kind of annoying. You'll have to understand it this week, but that's you'll probably have to implement it at some point, but at least just understand it this week. Yeah?
So you don't have to pass any arguments into those?
That is correct. These operations have implicit arguments of RAX or EAX or whatever. Yeah. Same thing with the other weird ones that I was talking about that extend into DX or RDX or so forth. Okay, multiply, divide. I'm just going to throw this up here. Do I really want to talk about it? No. Does anybody have any questions? No? Okay, good. Then we can move on. It's pretty straightforward. The reason why I'm actually going forward is because there's something really important at the end of this lecture I want to talk about, and I don't want to run out of time. So, branching. How cool is this? There's jump. No more of this BRZ0 junk, so we can just unconditionally jump. This is really cool. There's also a whole bunch of indirect jump operations, which is pretty awesome. You can do so much powerful stuff with them. So jump star, you can specify a register, and it will jump to the address contained in the register. Okay, that's cool enough by itself, but then you can do star parentheses, and now you take the value in the register, and you go look up in memory what is the value stored in memory at that location, and then you jump to that address. So you get 2 levels of indirection. Okay? This is super nice for implementing virtual functions if you happen to be compiling to C++ into machine code. That's nice. It's also really clever for doing switch statements. Okay? So there's a whole bunch of neat stuff you can do. You could implement continuation passing. Okay, so you could do something like that if you wanted to. Trampolines, all kinds of other powerful flow control mechanisms at this level. Okay? Let's see. Everything else is a conditional jump. Now, it turns out you can do this with call as well. I haven't talked about, we talked about call in the previous lecture, but call has a similar indirect mechanism, so that's really good for it. So, we had this branching logic before, and we liked it because that's all we had. Like, now we can write loops. We're so cool. But the problem with this is that it would be a lot more useful to actually take the status output of the ALU and route that into the branching logic, not just try to hard code specific circumstances into our branching logic. So what we would prefer is this. Okay? So that we can take the status flags and then do stuff based on the values of the status flags. And so this is basically how processors really work. Okay? We take the status output and we do conditional operations. Okay? So you have rflags, and these are really the only ones we care about in CS24. There's a lot of other ones you start caring about in 124, but these are the only ones we care about. Carry flag, which is unsigned overflow. Sign flag, that'll tell you whether or not the value is negative. Overflow flag, that's signed overflow. And zero flag, that'll tell you if your calculation ended up producing 0. Zero flag is kind of an optimization, but it's kind of a really nice one. Now, like I said, the conditional jump instructions will use these. And the nice thing is that all the arithmetic operations, I should say there are caveats, there's special cases, but the arithmetic and logical operations modify these flags. So basically you can always do math, and then do a conditional jump based on the results of the math operation. Okay, so that's kind of a neat thing. There's also two special instructions, compare and test. Compare and test do math, but that they don't store the answer. They just update the flags. And so these are really useful for doing test and then branch kind of code. Okay, so compare is a subtract, don't store the result, and test is a bitwise and don't store the result. Okay, and so then they modify the flags and nothing else. Okay? We're going to talk about these in more detail in the future, but we're going to talk about a few things right now. Conditional jumps basically can only specify a literal label, and so you can't do indirect conditional jumps for whatever reason. So here's some simple examples. Jump if equal, that's what the E stands for. Equal happens when the 0 flag is 1, because if you have two equal values and you subtract one from the other, you get 0. It's magic, right? So you could do compare, and if the 0 flag is 1, then you know they're equal, and then you can jump somewhere. Okay? Jump if sign, jump if not sign. So this will jump somewhere if a value is negative or non-negative. Okay? You have jump if carry or jump if not carry. So you can use this for testing for unsigned overflow or other just random things, because some things will set the carry flag just in general. Okay? A lot of the firmware, the older school firmware that we don't really use anymore, but all the way up until maybe a decade ago, carry flag was how they indicated errors on calls through the firmware. Okay, and then you have overflow or not overflow. So this is a signed overflow test. Okay, so that'll involve more than just the carry flag. Okay, jump if greater. So again, if you really like typing and assembly code is bumming you out because you just don't have enough characters in the instructions, you can do things like jump if not less than or equal, if you like. It's the same thing as jump if greater. But this is a signed comparison. You have jump if greater or equal, jump if less or equal. And these look at a combination of 3 flags. 0 flag for telling if things are equal, and then the combination of the carry flag and the overflow flag. Okay? Because that'll tell the processor if this thing is greater or less than the other value. Okay? I'm not going to go into how it's done. It's in the book, and I don't like talking about it. So we're going to skip over that. But the important detail here is if you need to do signed comparisons, you have help. Jump if greater, jump if less. Everybody got that memorized? Because the next thing to talk about is jump if above or jump if below. Okay? Above and below are for unsigned, and greater or less are for signed. Good luck, everyone. Let's wish us all luck. So there's also fun, long versions of those. Okay? But these are unsigned, so they basically only look at the carry flag and the 0 flag. They don't care about the overflow flag because they're not considering signedness at all. Okay? So again, pay attention to this. If you're using ints in your C code and you have to translate that into assembly code, use jump if greater, jump if less. If you're working with unsigned ints, use jump if above or jump if below. Okay? So it's important to be aware of these things. All right? Yes, question?
Does this jump if label is above and below something, or if something is above and below label?
So label basically just says where to go if the condition is true.
Then what are we?
Yeah, so remember that assembly code instructions are simplistic, minuscule things, and so these are communicating with each other through the registers. So typically you'll do an add or a subtract, and then do a conditional jump, or you'll do a compare, and then you'll do a conditional jump. So you'll have a sequence of these operations that are strung together to do the thing. Okay? Alrighty. Let's see. Conditional set. These are, I'm going to spend a little tiny bit of time talking about these. Basically, these are really helpful when you need to extract the value of a bit from the flags register to do some computation. Okay, you will run into this on probably 2 different assignments where you want to say, hey, what's the carry flag? Set this thing to 1 if the carry flag is set. Okay? And so you have these various operations that you can use. Okay? You've seen them. That's all we're going to talk about them. They're not complicated, and certainly you can ask me or the TAs if you're curious. But these are really useful in cases where you need to, store a value based on the contents of the flags. All right, let's see. So enough about that. But wait, there's more, and it's insane. Like I said, the X86-64 instruction set architecture manual that Intel produces is over 4,000 pages. Okay, and this is like 35 of those pages. So there's a lot more where that came from. Okay, so yeah, if you have the book and want to do the reading, there's a lot of information in there. Okay. All right, and you can always, test us, see how well we know our instruction set architectures. What is this instruction? What's that instruction? And we'll certainly try to figure it out for you if you can't figure it out. Okay, question?
It's an Intel manual with all the syntax included?
Yes, that's what I was saying before. Since it's the Intel manual, it's Intel syntax. Good luck, have fun. So I'm sorry, but that's just the way. That's why it will be a little bit of a challenge to read that stuff. But just you can do the translation in your head. It's not hard. Okay. I've been doing this for years, and it hasn't driven me insane yet. Okay. People are like, what? Okay. Let's talk a little bit about the really important thing that I mentioned. We'll see if we can cover it in 6 to 7 minutes. We started talking about how you actually build higher level abstractions. Things like subroutines, right? Crazy high level abstractions. Now, there's a lot of different conventions that we could choose from. We're going to be really simple and stick with C. Okay? Let's not get fancy until like 2 weeks from now, and then we can get a little bit fancier. So, it turns out that this is straightforward to implement. We had this set of problems we had to solve. How do we pass arguments and return values? How do we get from the caller to the callee, the subroutine, and then get back? And how do we isolate the state between the caller and the callee? Okay, those were the problems that we had to solve. And so there's specific there's facilities the processor provides to make this straightforward. So you have a stack pointer, RSP. We've talked about it. Okay, grows downward. Since we only push 64-bit values, it always goes down by 8. So keep that in mind as we look at junk. Okay, and so those behave the way that you would hope. You have RBP, which is the frame pointer for if you want a stack frame. And then you have call, which transitions to a particular address, but it pushes the next instruction pointer onto the stack before doing so. And then you have ret, which pops the top of the stack into the instruction pointer. Okay? Just like we talked about last time, none of this is horrifying unless you are already horrified. Okay? So let's see. Lots of different ways to organize stack frames. This is where the C word comes in again. Convention. It's not theory, and there's not like underpinnings. It's just everybody's got to do it the same way for it to work properly. Okay? So basically, the convention that we will be following is used by everybody on 64-bit Intel x86 processors. Because they realized that when we had 32-bit processors, we had like 4 or 5 ways of doing it, and it was chaos. And so everybody follows the System V or System 5 AMD 64 ABI. Okay? ABI stands for Application Binary Interface. Okay? So the caller and the callee both have to coordinate this operation because you have 2 shared resources. You have the register file and you have the stack. Okay? So the convention says who's responsible for what parts of this handoff. Okay? So who sets up parts of the call, what needs to be saved, who needs to save it, how do we get a return value back, and who cleans things up. Okay? So that's why there's a summary, because I find it useful too. So you can refer to the summary sheet that I put on Moodle, and it'll be really helpful. Caller has to provide the arguments. That's like an obvious statement, right? The callee has no idea where to get them from. Since we have so many registers, 16 is actually not a lot. If you're on a RISC processor, you can have tons and tons of registers. But X86-64 has 16, so we can actually pass some of the arguments in registers. And they're in, again, some weird, bizarre ordering. So RDI is the first argument, RSI is the second argument. If you only have 2 arguments, those are the only 2 registers that you would expect things in. But you know, as you need more arguments, you can use these registers. Okay, was there a question or?
No.
Okay. If you have more than 6 arguments, they have to be pushed onto the stack. This is extremely rare in Unix programming. Okay, so this is really nice. Basically, you can pass all of your arguments in registers and not have to think about the stack very hard. Okay. All right. Let's see. Primitives may be ints, or they might be. Oh yeah, question?
Is there an advantage of using the register to pass arguments as opposed to using the stack?
Yes, there is a giant advantage for using registers instead of the stack. Talking to the stack is slower than talking to registers. We'll talk a lot about why that is in week 5. But even just looking at the whole question of having to push things onto the stack and pop stuff off the stack, I have to do math, I have to store stuff in memory. It's more work than just stuffing something in a register and calling a function. Yes, good question though. Okay, so yeah, we're going to pretend that everything is an 8-byte quad word, because that's just simple. And so that's why the addresses are weird. They're like 98, 90, 88, 80, so forth. Because remember, there's also A, B, C, D, E, F for these guys. Okay. And so the arguments are pushed in reverse order from their appearance in C and C++ code or whatever higher level language you're using. Basically, the benefits are if the function doesn't know to expect them, it won't break the function. So if somebody pushes 15 arguments to a function that takes 12 arguments, it doesn't care because it doesn't even know those are there. Okay? Also, the higher the offset, the further along the argument is. So this is a convention, again, that people have settled on, and it's actually leveraged quite heavily in operating system implementation. Okay? Let's see, use call to invoke the procedure. So notice that pushes the return address onto the stack. And if the callee wants a frame pointer, we talked about frame pointers. If we're using the stack, then you can use RBP for that. Now, this is an example where we need to save the old value because the caller might have been using RBP. Okay, so we push it onto the stack, and so we end up with code like this frequently. Push the old value onto the stack, set up my frame pointer. Okay. So now we have 8 RBP. Return address, right? 16 RBP. Well, if 6 arguments weren't enough, then that's going to be argument 7, and so forth. Okay? So this is how we get into the function. This kind of thing that you see is an example of whether or not a register is callee save versus caller save. Okay? So we have to think about how we preserve these registers just in case the caller might have been using one. So you have a collection of registers that must be saved by the callee if the callee changes them. If it never touches them, it doesn't care. Okay? But if you modify RBP or RBX or R12 through R15, you are responsible for saving them and then restoring them. So those are called callee save. Then you have caller save. Everything else that's not mentioned there is caller save. If the caller wants to preserve the value, they've got to save it before invoking the function. Okay? Now RSP doesn't appear in either one of those because RSP is relative to the stack. And remember, we had this rule that the stack should be in the same state when we leave the function as it was when we enter it. So RSP will kind of end up being preserved. I mean, there's a careful coordination there, but it doesn't really technically fall under callee or caller. Okay? Let's see. I know we're out of time, so I'll just talk about this last thing. We're going to talk about returning ints, longs, and pointers. That's all we care about in this class. So in this case, we return the result in RAX. Okay? So basically, we set RAX to whatever we want to return, and then we have to go back. Now the question is, who gets rid of the stuff on the stack? And again, the caller is the one who knows how many arguments they put on. The callee doesn't necessarily know. So in this convention, the caller is responsible for cleaning up the stack. Okay, so that's a nice, safe way of doing it. I'll tell you, and just leave this on the table for you to consider, that in 32-bit, in Linux, the caller was responsible for cleaning up the stack, as one would think. On Windows, the callee was responsible for cleaning up the stack. Yay, how fun was that? Okay, thankfully we've all moved in a better direction. Okay, any questions? We got to wrap it. I know we're out of time. The rest of the details are in the slides online, so I'll see you next time.